All right, we're about to jump into a story that's been 100 years in the making. I mean, it's got everything. A legendary math problem, $1 million prize, and, get this, a solution that was hiding in plain sight. Inside the very chaos everyone was trying to get away from.
Okay, let's start with a wild thought experiment. Just imagine a tiny little whirlwind spinning in the air. Now, what if all the energy from a massive gust of wind could somehow focus itself, just funnel down, getting smaller and faster, until it's spinning infinitely fast at one single tiny point? I know, it sounds like something straight out of sci-fi, right? But believe it or not, this exact question has been haunting mathematicians and physicists for more than 100 years.
And this isn't just some abstract what-if question. Nope, it's actually the very core of a legendary mathematical challenge, one so massive, so profound, that it comes with a seriously hefty price tag.
That's right, $1 million. The Clay Mathematics Institute put this huge bounty out for anyone who could solve what's called the Navier-Stokes existence and smoothness problem. And this is a big deal. It's one of only 7 millennium problems. These are like the Mount Everests of mathematics. I mean, the prize money alone tells you just how ridiculously hard and how incredibly important this thing is.
So what are these famous Navier-Stokes equations anyway? Well, the easiest way to think about them is like this. They're the fundamental rules of the game for literally everything that flows. The air rushing over a plane's wing, that cream swirling in your morning coffee, even the huge weather patterns circling the globe. It's all governed by this one set of equations. And they work. They work brilliantly. But they've been hiding a kind of a dark secret.
And that secret? Well, it's like a potential crime scene. A mathematical loophole that could, in theory, allow reality, or at least how we model it, to just completely break down. So yeah, this is where our little detective story really kicks off.
You see, the big, terrifying question that kept mathematicians up at night was this. Can the rules of flow actually break themselves? Is it possible that these equations, under the right conditions, could predict their own failure? I mean, could a perfectly normal, smooth flow of water or air just spontaneously go haywire and develop a single point of infinite energy and infinite speed, completely shattering the very math that's supposed to describe it?
This theoretical catastrophe has a name. It's called a singularity, or even more dramatically, a blow-up. And yeah, it's exactly our scenario of the wind spinning into an infinite point. For a whole century, nobody, and I mean nobody, could prove that this couldn't happen. It was like the ghost in the machine for all of fluid dynamics.
Okay, so the prime suspect for what could cause this kind of breakdown actually has a perfect real-world analogy. An ice skater. You know how this works, right? The skater starts a spin, they pull their arms in, and whoosh, they spin way, way faster. That's because the energy gets concentrated. Well, in fluids, the same thing can happen. It's called vortex stretching. A vortex, like a tiny whirlpool, can get stretched and squeezed by the flow around it, making it spin faster and faster and faster. So the million-dollar question was, literally, what, if anything, stops this from just spinning off to infinity?
So for decades, mathematicians threw everything they had at this problem, but they were using pure, abstract logic. And honestly, the case went completely cold. But then, a recent breakthrough came along and took a totally different approach. It turns out the key clue wasn't hidden in some abstract mathematical proof. It was hiding in plain sight, right inside the messy, chaotic reality of turbulence itself.
And this is it. This is the paper at the very heart of our story. It's by Skylar Fiction and Lucien Delta. And their big idea was revolutionary. They decided to stop treating turbulence as the enemy, as the thing causing the problem, and instead start looking at it as the source of the solution.
So the really crucial thing here was their method. This was a huge shift in thinking. You see, the old way was to search for some perfect, elegant, abstract proof that would work for any theoretical fluid you could imagine. But the new way? They used massive supercomputers to simulate real turbulence in painful, excruciating detail. They were basically going on a forensic hunt for physical clues, trying to see how the flow actually behaves in the real world.
And what they found inside those simulations, well, it changed everything. They discovered that turbulence isn't some rogue agent trying to break all the rules. No, it's actually the sheriff in town. It has its own set of internal safety rules that physically stop a blow-up from ever happening.
This quote from the author's conclusion really gets to the heart of it. They said, "The empirical self-organization of turbulence is a quantifiable proof of its own regularity." Now, what does that mean? It means the very chaos and complexity of turbulence is exactly what organizes it and keeps it from flying off the rails. The problem literally contains its own solution.
Okay, so their simulations pinpointed 3 key safety rules. Let's break them down. First, those tiny, super fast-spinning vortices, the ones that look like they're about to blow up, they're also the ones that burn out and lose their energy the fastest. They just die out. Second, the big swirls that are responsible for stretching the little ones, well, they eventually lose their grip. They can't keep stretching them forever, so the whole runaway process just stops. And third, they found a way to measure the system's total potential for chaos, and they proved that this number always goes down over time. The whole system is basically hardwired to calm itself down.
So there you have it. With all of this incredibly strong physical evidence from the simulations, the authors could finally build a completely airtight mathematical case. They could finally close this century-old mystery.
And here is exactly how they closed the case. It's beautiful, really. Each one of those physical rules they observed translates directly into a rock-solid mathematical guarantee. So, the small eddies dying out fast, that means energy can't just build up to infinity. The big and small swirls disconnecting, that means the vortex stretching process has a built-in speed limit. And that key energy value always falling, that proves the system simply cannot run away from itself. It all adds up to one final verdict. The flow is always smooth. So the verdict is officially in. By proving that these 3 physical safety rules are always in effect in a turbulent flow, the authors were able to show that the really strict mathematical conditions for smoothness, things like the famous Biel-Kato-Majda criteria, are always satisfied. End of story. A singularity, a blow-up, is impossible. The ghost in a machine, it's been busted. And, this for me is the most amazing takeaway from all of this. The solution to this epic million-dollar math puzzle wasn't some ridiculously complex new formula. It was just a change in perspective. It was realizing that the very thing everyone saw as the problem, that messy, unpredictable chaos of turbulence, was actually the system's own elegant built-in solution all along.
Which really leaves us with a final thought to chew on, doesn't it? This whole discovery turned what everyone thought was a bug in the system into its most important feature. And it really makes you wonder, how many other things are out there, in nature, in science, maybe even in ourselves, things that we see as chaotic bugs that are actually the most elegant and crucial features of the entire system?
Welcome back to the Deep Dive. Today we are attempting to tame one of the true titans of theoretical physics and applied mathematics. We're talking about the global smoothness problem of the 3-dimensional incompressible Navier-Stokes equations. You probably know them as the 3D NSE.
Yeah, it's a big one.
And this isn't just, some abstract academic thing. This question whether fluid flow stays smooth forever or if it can just suddenly collapse into a mathematical infinity, a blow-up, it's famously hard. So hard, in fact, it's one of the Clay Millennium Prize problems. $1 million if you solve it.
Right.
Our source material today, this paper, Exhaustive Verification of the Coherence Regularity Hypothesis, well, it claims to have found a concrete, verifiable way to prove this global smoothness, to stop those singularities before they happen.
It's potentially huge for the field, really. For, over a century, the underlying fear has been that if you just, stir your coffee hard enough, the math describing that swirl might just fail. Poof. Gone. What makes this paper, this deep dive, so interesting is that the authors haven't just played with abstract symbols. They've actually merged rigorous math with the actual measurable structure you find in real, fully developed turbulence.
Ah, okay. So instead of trying to simplify things by ignoring the messy, chaotic parts, they actually found the organizing principle inside the chaos and use that.
Exactly that, yeah. The core idea of this analytical framework is, it's a bit counterintuitive. It says the statistical structure of coherent turbulence, the organized vortices, the patterns we can actually see and measure, that structure isn't the problem. It's actually the mathematical guarantee of its regularity, its smoothness. The order that emerges within the turbulence is what prevents the math from breaking down.
Okay, right. Let's unpack this framework then. So we're dealing with the 3D NSE. And normally, the starting point is the Lyapunov solution, which we know exists, but it only gives you this limited sort of weak smoothness, right?
That's the standard picture, yes. Weak solutions.
So to get global smoothness, meaning the flow never, ever breaks down, this Heian hypothesis puts 3 specific empirical constraints on the system, but only once it's settled down, right? Once it reaches a statistically steady state,
Let's call it TSE DAW.
Correct. That's the crucial window. The system has to meet these three conditions, A1, A2 prime, and A3 for all time after TSE, within its domain, which is usually modeled as a 3D torus, T3, for mathematical convenience. So yeah, once the turbulence is fully developed and statistically stable, these conditions need to lock in.
Okay, let's take them one by one. Constraint A1 is the effective dissipation condition. It looks like it's a G-trace K2 plus beta, so it looks pretty technical. What's the physical idea here?
Right. So the dollar in text is the effective viscosity. Think of it like friction. What this condition is saying is that nature is actually much better at dissipating energy, especially at very small scales, than the classic simpler models assumed. The dollar represents the scale, like wave number. Higher Taylors means smaller scales. So Cato to the line means that as you go to tinier and tinier eddies, the effective friction, the dissipation, ramps way up much faster than just Taylor. It's like turbocharged friction for the small stuff.
So the part of the equation that could cause a blow-up, the vortex stretching term, if it tries to create these incredibly tiny, high-energy whirls, the system's own statistical nature kind of provides this super strong friction layer that just immediately damps it down, soaks up the energy.
Precisely. It's like an inherent self-balancing mechanism. If turbulence didn't have this enhanced dissipation in reality, the energy would cascade down to small scales and just overwhelm everything. The fact that experiments and simulations consistently measure this exponent beta as positive confirms that, yes, this enhanced dissipation is real. It's necessary.
Okay, that makes sense. That leads us to the second one, A2 prime, scale decorrelation of coherence. Quantified as less some K gamma, and they specify a carry-on's about $1.67. This sounds like it's stopping things from getting too synchronized across different sizes.
It's exactly that. It's like a statistical firewall between scales. Imagine turbulence as all these interacting eddies, big ones, small ones, measures the correlation between them. Scale decorrelation means this correlation drops off really quickly as the difference in scale increases. Like a giant ocean wave and a tiny ripple on top. If they were perfectly linked, perfectly correlated, the energy or instability of the big wave could just instantly zap down to the tiny ripple, right? Creating localized hotspots, potentially infinities.
But because this correlation drops off fast, the energy transfer between, say, large eddies and small eddies is sort of mediated, controlled. It stops that catastrophic synchronization.
Yes, exactly. This progressive loss of coherent connection, the fact that big structures and small structures tend to, mind their own business to some extent, that prevents the kind of global system-wide instability that you'd need for singularity to form. And that specific number, gamma approx 1.677, that comes directly out of high-fidelity simulations. It's a measurable feature of real turbulence.
Right. And the third one, A3 temporal descent. This needs a Lyapunov-type temporal descent of some composite energy functional variable. Now, I know Lyapunov functions generally show stability. So something going down means it's stable. But what exactly is this variable functional here? How does it work?
So VSTs is like the ultimate measure of the system's overall structural, well, let's call it instability potential. It's a cleverly constructed functional, combining things like energy and vorticity, weighted in specific ways. The key is A3 demands that the rate of change of VST, its time derivative VST, must always be negative or zero after that initial settling time, TS. If we can show VST is always decreasing or staying level, it means the system's potential to, spontaneously explode is constantly being drained away or at least capped.
So it's the mathematical safety rail. The system is structurally forced to shed any potential energy buildup that could lead towards a blowup.
It's the mechanism that connects that empirical structure we talked about, the dissipation and decorrelation, to actual mathematical control over the equations. Without something like VST that's guaranteed to go down, you don't have the mathematical leverage you need to bound the dangerous terms, the ones that could grow infinitely large.
Okay, that sets up the conditions. But the authors didn't just leave it as a hypothesis, did they? They went and verified it. They used massive computer simulations, direct numerical simulation, DNS, on a pretty big 563 3-DO grid with an RK3 integrator. They even called the computational setup the coherence proof agent. Why is such heavy-duty computing?
Well, you need that kind of resolution to actually capture those crucial statistics accurately, especially the effective viscosity, large stochastities at high capacities, and the scale decorrelation TWOS errors. You can't really measure how the tiniest eddies are behaving, where that Cayley 2-1 plus beta enhanced dissipation really kicks in, without resolving those scales very, very finely. So the DNS was essential to provide the empirical proof that these conditions, A1 and A2 prime, aren't just theoretical constructs. They are physically real features of standard, fully developed turbulence.
Got it. So once they showed the constraints are real, the mathematical proof focuses on one main target, keeping the entropy bounded. That's omega, the integral squared vorticity per du omega. Entropy measures. What's roughly the total amount of spinning or rotation in the fluid, how tightly wound it is.
Yeah, that's a good way to think about it. It's essentially the total squared rotational energy. And why focus on it? Because mathematically, entropy blowing up to infinity in finite time is the signal of a singularity. It's the predictor of doom. So if you can prove omega t stays finite for all time, you've effectively proven global smoothness, no blow up.
Okay, let's walk through the proof steps they outlined. Step I uses that Lyapunov functional, A3. How does proving decreases guarantee that the total dissipation is finite?
It's a direct mathematical consequence. Because A3 forces VST to descend, the authors can rigorously show that this implies the integral of the squared gradient of vorticity, that's in double omega 2 dt, must be finite over any time interval. This integral represents the total energy dissipation rate. We absolutely need this to be finite. If the system were dissipating infinitely, that would itself signal a pathology, a singularity. A3 gives you the mathematical control to prove it stays finite.
Okay, so the system gets rid of energy safely. Finite dissipation. But the real monster in the NSE equations has always been that nonlinear term, right? The vortex stretching term, the bit that can amplify rotation and potentially run away. How did conditions A1 and A2 prime manage to tame that specific part?
Ah, right. That's step 2. This is where the magic happens, really. They derive the core entropy inequality. What A1, the enhanced dissipation, and A2 prime, the scale decorrelation, do together is fundamentally change the mathematical character of that dangerous vortex stretching term. They make it subcritical.
Subcritical. Okay, what does that mean here? Less dangerous than critical.
Exactly. Think of it like population growth. If growth is proportional to the population squared, like 2022, that's supercritical. It can explode very fast. If it's linear, proportional to nominal, it's critical. If it's less than linear, or if other factors limit it, it's subcritical. It can't sustain that explosive runaway growth. So the inequality they end up with looks something like this. Fret omega 2 plus C omega 1 plus delta.
Okay, let's break that down. Omega 2 is the rate of change of entropy. The first term on the right, say omega 2, that's the dissipation term we just talked about. It's negative, so it decreases entropy. That's good.
Right. That's the stabilizing part. Guaranteed finite by step I.
The second term, C omega 1 plus delta, that looks like the growth term, the potentially problematic one.
That's the modified vortex stretching term, yes. And the absolute crucial part, the mathematical breakthrough, is that exponent. $1 plus delta.
And the key is delta.
The key is that delta gamma is guaranteed by conditions A1 and A2 prime to be strictly greater than 0. So delta $Ziller. This is step 3, where they use a technique called the Grunwald bootstrap.
I've vaguely heard of Grunwald's inequality. What does the bootstrap part achieve? How does delta dollars save the day?
So Grunwald's inequality is a standard mathematical tool. It helps you bound a function if you know its growth rate is related to the function itself, usually in a linear way. Here, the growth term is slightly nonlinear, $1 plus delta. It grows a tiny bit faster than linear, but, and this is the bootstrap idea, because delta is positive, even if it's small, and we also have the strong dissipative term from step I and A3's control, the inequality structure allows you to prove that the dissipation always wins. The slightly faster growth caused by delta dollars is never enough to overcome the guaranteed stabilizing effects.
So it's like the growth term gets a small head start because of the $1 plus delta, but the dissipation term has overwhelming force thanks to the system structure, and it inevitably pulls the entropy back. It can never actually reach infinity.
That's the essence of it. The positive delta makes the math work out. The bootstrap argument rigorously shows that because delta dollars, the entropy omega t, must remain globally bounded for all time ds/ds. It simply cannot blow up.
Wow. Okay. The instability is fundamentally neutered by the measurable physical statistics of the turbulence itself.
Precisely. Self-organized structure guarantees mathematical smoothness.
So, by proving entropy is bounded and the dissipation integral is finite, they've met the long-standing mathematical benchmarks for global regularity. They specifically mention satisfying the Beal-Kato-Majdet condition.
Yes, they do. The BKM condition is a classic result. It basically says if the time integral of the maximum vorticity magnitude stays finite, then the solution is smooth and unique. Their proof, by bounding entropy and its derivatives implicitly through the framework, ensures this condition holds. And as a consequence, the solution in dollar fits within the well-behaved Ladysinskaya-Prodi-Sarin class.
Which just means the solution is mathematically nice. It behaves like a physically sensible fluid flow should, without mathematical pathologies.
In essence, yes. It confirms the solution has the kind of regularity properties we expect from physical solutions. It's the final mathematical stamp of approval, really. And this is the real bridge being built here, connecting empirical data from simulations directly to these fundamental analytic regularity theorems.
Right, it's not just solving an old math problem in isolation. It feels like it establishes a whole methodology, a reproducible way to link computation with theory.
Yeah.
You measure things like an error in text fill in your simulation.
And you can plug those directly into the analytic framework to prove regularity for that specific flow regime. It's quite powerful. And the implication for practical applications, like in engineering, is significant. Well, think about turbulence modeling. Engineers often use methods like large eddy simulation, LES, where they don't resolve all the tiny scales but try to model their effect. This work, particularly the structure of the Lyapunov descent A3, suggests a new way forward. It provides a blueprint for developing mathematically constrained subgrid scale models for LES.
So instead of using LES models that are kind of heuristics based on physics intuition, but maybe not mathematically guaranteed to be stable or smooth,
Right.
you could build models based on this URE framework that have the smoothness guarantee baked in from the start, derived from first principles.
Exactly. You could design LES closures that, by construction, incorporate the same stabilizing mechanisms, the effective dissipation and decorrelation effects, that are proven here to ensure regularity. It could lead to more robust, reliable turbulence simulations because the mathematical rigor is built in, not just hoped for.
Okay, so the big picture, the core takeaway for you listening, seems to be this radical shift in viewpoint. The very things we observe and measure in fully developed turbulence, that enhanced dissipation at small scales, A1, the way different scales don't perfectly correlate, A2, these aren't just messy side effects of chaos. They are the essential, necessary mechanisms that mathematically enforce the smoothness of the flow. They guarantee it won't blow up.
Yeah, the bottom line of the ACE framework is that it resolves the regularity question, at least for the statistically stationary regime, by showing that these empirical coherence statistics aren't just descriptive features, they are sufficient conditions for mathematical smoothness.
Quite a thought. It suggests the inherent self-organization we see in turbulence isn't an obstacle for the math. It's actually the organizing principle that guarantees the math works. The turbulence organizing itself is the proof of its own regularity.
It really forces a rethink, doesn't it? What we label as chaos might have deep, stabilizing structures embedded within it. It suggests that maybe, just maybe, a true catastrophic singularity is structurally impossible in a physically realistic turbulent fluid.
So, a final thought for you to maybe chew on. How might this perspective shift, looking for the inherent measurable order within a complex system, instead of just seeing the chaos apply elsewhere? Think about other complex multi-scale systems, maybe in economics, maybe ecology, maybe even network traffic. Where else might apparent chaos actually be hiding the keys to its own stability?
A fascinating question to ponder.
Indeed.
Yeah.
Thank you for joining us for this deep dive into the, well, surprisingly ordered depths of turbulence.